just given the definition and some easy examples and very basic definitions and properties. I will proceed with that a little bit. So the next thing I wanted to introduce was polynomial rings, which is a very important example of rings, or rather an important example how one makes a bigger ring out of a smaller ring. So I give this slightly informal definition, but I think it's very clear. So polynomial rings. So we start with a ring. I take a unitary ring to make it easier. Let R 1. So then I have to say what a polynomial with coefficients in R is. So a polynomial F say in a variable X with coefficients in R is an expression, so I define it as something formal, just as something writes down, F equal to A0 plus A1X plus and so on, plus say an x to the n, which I can also just write sum I equals 0 to n ai xi. So with ai elements in our ring and n some non-negative integer. Okay, so for me, a polynomial is such an expression. It's not quite finished. But so in school or in the beginning of the studies for you, usually a polynomial will be a map. No? So this f of x, like this would be you put some number for x and then you get an expression. But here we want to stay at this formal level because that's what we need. So I have to still say, it's not quite finished. I have to say what it means for two polynomials to be equal. It's not equal when they are equal on the nose, but slightly different, namely terms where the coefficient is 0 don't count. So, anyway, we call ai the coefficient of x to the I of f, as you are used, and then two polynomials. So say f sum I equals 0 to n ai x to the I, and g equal to sum I equal 0 to some other number m. Bj x to the j are called equal, are equal by definition, and I just write f is equal to g, and they are for me the same thing. If, well, we have these. This goes here until n, this goes until m. One of the two numbers, n and m, will be bigger or equal to the other. So can assume that, say, the second one is bigger. So if g, when m is bigger or equal to n, we have that j is equal to 0 for j bigger than n. So all the extra terms adjust with 0. And the terms before are equal. ai is equal to bi for I smaller equal to n. Okay? So for me, a polynomial is just that, such an expression. So further, as one can also already see here, x to the 0 I somehow also am willing to leave out. And so I say that, so we denote Rx, set of polynomials in X with coefficients in R. And we can also, so we identify this A0 times x to the 0 just with the element A0 in R. So somehow x to the 0 is supposed to be 1. And so with this, we have that R0, R is a subset of X. And the polynomial of this form is called a constant polynomial. Okay. So this is just this basic definition. I should maybe, I had already remarked this. So for us, a polynomial, so if we have a polynomial, so if f in Rx polynomial, say f equal to sum I equal 0 x to the I, then obviously f defines a map by replacing the variable x by an element of R, so which I could call, well, anyway, so from R to R, any element B is sent to sum I equals 0 to n ai b to the I. So the map defined by the polynomial. But for us, these two things are not the same. So this is a polynomial, and this is the map defined by the polynomial. And in particular, from our point of view, there are many more polynomials than, there can be more polynomials than there are such maps. For instance, if R is just, for instance, the Z2, this has just two elements, there are still infinitely many polynomials in Z2 of X, but there are very few maps from Z2 to Z2, and so there can be very few maps given by polynomials, but only four maps from Z2. No, there's only 4 ways how you can map, find a map from Z2 to Z2. And so for us, there are many such polynomials. Okay, and that's why we have this formal definition, not like you do in school. Okay, so I also should, so where am I? Yeah. So obviously we want these polynomials to form a ring, so we have to define addition and multiplication. So for the addition, it's obvious. You just add the corresponding coefficients. And for the multiplication, you will do, you treat this x as if it was something in a ring, and you just multiply by it. X to the I times x to the j is x to the I plus j. And then you use formally the distributive law, and this gives us the definition. And so we get then the following definition. So we define a ring structure on Rx, namely for f equal to sum I equals 0 to n ai x to the I, and g from sum, say also I equal 0, I equal to 0 to n b I x to the I. We can always assume that this goes to the same number because we can add 0 times x to the I at the end to make them match. We have define f plus g is just defined by summing the corresponding coefficients. And the product, write this formula. This is, say, the sum from I equal 0 to, in this case, n, sum j, I don't want to write it, so j plus k is equal to I, a j times k times x to the I. And so this is precisely what happens if you just formally multiply this out and then collect the terms. But here, this is our definition. Okay. So now, with this definition, you can check. This is an exercise just in the definitions that Rx will be a ring with 1. So a unitary ring with this definition. And so obviously the 0 element, so the neutral element for the addition is element 0 in R. The unit element so the neutral element of multiplication is 1 in R. And okay, and furthermore, if R is commutative, then so Rx. So these are completely trivial verifications. I think it would be a certain amount of effort to kind of exit all out here. For instance, the associativity, the distributive law and all that, but it's all trivial. You just write it down and then it's there. So I will not do it. So usually as in school or whatever, one has a slightly simpler notation. So one doesn't necessarily write terms where the coefficient is 0. And so, for instance, so notation usually of terms with coefficient 0. So if we have something like 7 times x to the 0 plus 5x plus 0 times x squared plus 0 times x to the third plus 1 times x to the 4, we just write this as, write this as 7 plus 5x plus x to the 4. We also don't write the 1. Okay, as one is used to. Okay, so this is this simple thing. So now, so one property that, so one important invariant of a polynomial is its degree. It's the degree, so the highest power I for which the coefficient ai is non-zero. And so let's introduce this. So let f be a non-zero polynomial. Write f equal to sum I equals 0 to n ai x to the I with a to the n different from 0. We can do that by leaving out the any zeros which come afterwards. And then n is called, so say, I write it the degree of f n is called of f. So obviously by definition, it's clear that the degree of f is a non-negative integer, and the degree of f equal to 0 if and only if f is a constant polynomial. I mean, non-zero constant polynomial. Note I have not defined the degree for the 0 polynomial. So, and we call, if n is the degree here, we call an the leading coefficient of f. Okay, so this is this thing. And then, so this definition is useful to show, for instance, that if our ring to begin with was an integral domain, then the polynomial ring is also an integral domain. It's a very easy observation. Mark. Let R be an integral domain. Then, and say f and g non-zero polynomials. Then, first, product f times g is also non-zero, and in fact, the degree of f times g equal to the degree of f times the degree of g plus the degree of g. And second, Rx is an integral domain. And what's the third? Third is also a simple fact. If I take the units in Rx, same as the units in R. Oh, so we know that, so we had that R was a subset of Rx, and in fact the subring of Rx of constant polynomials. And then I say that I claim here that a polynomial can only be a unit if it is a constant polynomial, and that constant is a unit in R. Okay, so it's also clear that 2 follows directly from 1, because to be an integral domain means if I have 2 non-zero elements, then their product is non-zero, which is said here. So we only have to show 1 and 3. So let's prove it. So we take f, write f down, f equals sum I equals 1 to n ai. X to the I, 0 to n, g sum j equals 0. M x to the j, and I want the degree of f to be n and that of j to be m, so we have a n different from 0, m different. Then if I apply the rule for multiplication, we have that f times g is equal to the sum over all, say, k from 0 to n plus m. The only way I can reach, and the maximal power I can reach is n plus m. So ck, k, where ck is, according to this thing which I wrote down here, the sum over all whatever L plus S is equal to K, AL times BS. Or whatever, maybe I take I and J, so sum over all I plus J is equal to K, I J. Now, in particular, if I look at this, to get n plus m, there's only one possibility, namely that ai is equal to n, that I is equal to n, and b is equal to m. So here, obviously, I smaller equal to n, j is smaller equal to m. So in particular, we have that C n plus m is equal to a n m. And a n and b m are both non-zero, and R is an integral domain, so this is different from 0. Is integral domain. So, and then, so we see that the coefficient of x to the n plus m is non-zero. And so, in particular, it follows that f times g is non-zero. And so the highest possible coefficient is n plus m, and that coefficient is non-zero. So the degree of n of f times g is equal to n plus m, which is the degree of f plus the degree of g. Okay. So this was this simple fact. The last one, last statement, is also a consequence of of this degree we introduced. So it's clear that from the definition that every unit in R is a unit in Rx. Just look at the definition here. This just means you multiply all the coefficients by this unit, and the inverse of that element will be just the inverse in R. Now, conversely, so let f be unit in Rx. Then it means it has an inverse. So thus is an element G in Rx such that f times G 1. But now I use this fact that the degree of the product is the sum of the degrees, so it follows f plus the degree constant polynomial 1, which is 0. And the degree is a non-zero, is a non-negative integer. So the only way that the sum of two non-negative integers can be 0 is that both of them are 0. So it follows that the degree of f is 0. That means f and g are elements in R. And f times g is equal to 1. That g is f to the minus 1, and f is a unit. Okay, so we will later have quite a lot of things to do with these polynomial rings. For the moment, I just introduced them. Now we will, for the moment, it's just another example of a ring, slightly more complicated than the others we considered, but will play a big role later in this course. Now I go a little bit on with the general observations. I want to introduce first division rings, but mostly fields, which will be the main topic of, say, last a little bit more of a third of the course, or maybe almost half, I don't know. So division rings and fields. So I'm not particularly interested in division rings. I just briefly mention them for completeness. So a ring, a unitary ring, so a ring with 1 is called a division ring if every non-zero element has a multiplicative inverse. So that means if R star is equal to R without 0. By definition, 0 can never be invertible. And so ring 1 is called a division ring if every non-zero element whatever A in R is a unit. Okay? So in other words, R star is R without 0. So as we have seen, if you multiply anything by 0, you always get 0. So therefore, 0 can never be invertible. So I just give, here I just give one example, which historically for some time was very important, but it's not really so super important. Anyway, these are the quaternions. Division ring, which is not a field, so a non-commutative division ring. So I just sketch it. So these are called H after Hamilton, who invented them. So they can be described as quadruples of real numbers. So I can write them as A plus BI plus CJ plus DK. So symbols like that, which just means you have a vector of 4 real numbers. having two such things are only equal if all these coefficients are equal. So R is the real numbers. And so the addition is component-wise. So that means just if I take A1 plus B1I plus C1J plus D1K plus the corresponding thing A2 plus BI plus C plus D2K. Well, maybe I shouldn't have written it. Anyway, it's given by summing up the coefficients. So it's A1 plus B1I plus C1 plus E1 plus A2, that's the point, 1 plus B2, J plus C1 plus C2. Okay, oh, sorry. Plus D2. Okay, so this is the most obvious way. You just sum them up as vectors in some sense. And the multiplication is done by formally applying the distributive law to these things and saying how the I, j, and k should multiply among each other. So multiplication is defined by the distributive law apply the distributive laws to these sums and the rule that I squared is equal to j squared is equal to k squared is equal to -1, and this is also equal to I times j times k. So if you kind of look at all the consequences of these, you get enough to determine what the multiplication of any two is. So as I said, I'm not particularly interested in this, so I just say it briefly. And so I just want to sketch why division ring, so why every element has a multiplicative inverse, every non-zero element, and that's, I just write down. It's a bit like it's very analogous, as you can also see from the notation for, so if you just write this, you get somehow the description of the complex numbers. And so it's very analogous to the complex numbers. You also have some kind of, every element has a conjugate where these, you replace these ones by their negatives. And if you multiply an element by its conjugate, you get something real. So let me, so we have the conjugate, which is A plus IB plus JC plus K. Conjugate is just defined to be A minus IB minus JC minus KD. And you can check that if you take, so the real numbers are a subset of this, are just those where these coefficients of I, j, and k are all 0. So we can check that if I take so if x element in H, then x times x bar is an element in real numbers. So nothing will remain with I, j, and k. And then you can therefore define, then you can see if you take the inverse of x, so the multiplicative inverse of x, you could write it like, how would you get it with the help of this? Well, you could say, okay, so this would be 1 over x, but now you just multiply, so to speak, formally by x bar, and so this is just x bar divided by this real number. So all the coefficients are divided by the real number. And this is the multiplicative inverse. Okay, so this was description of the quaternions. Maybe a nice thing that the quaternions give us also is one nice group. Namely, we can look at the group of all which one called unit quaternions. These are those where only one of these coefficients a, b, c, d is non-zero, and it's either 1 or minus 1. So Q8 is just the set of all plus minus 1, plus minus I, plus minus. So it's just a set consisting of these 8 elements, plus minus k. And then with the multiplication, so I take this, with the multiplication, quaternions is an interesting non-commutative group. 8 elements. So we had seen, for instance, if I have a group with p squared elements, it always has to be commutative, but this is the third power of a prime number, so it doesn't necessarily have to be commutative, and in fact we have this example. And I think one can also show, I didn't check it, that if you up to isomorphisms, the only groups of order 8 are Z8, Z2 times Z4, Z2 to the 3, and Q8. I hope I'm right. Well, anyway, it doesn't matter so much. Maybe there's also the dihedral group. Okay, so anyway, so that's, yeah, there should also be that. Okay, so but anyway, you can see, so this was this about the division rings. So what I'm much more interested in is fields, which are simpler. So a field is just a commutative division ring. So the multiplication is commutative. Division called fields. I will instead, so this is the definition, but I will write it also explicitly to have it once, to have the axioms there written explicitly. So what does that mean if we write down all the ingredients? So a set R, 2 binary operations. So plus and times is called a field, and so it has 2 binary operations, it has 2 distinguished elements, namely the neutral elements of addition and multiplication, and elements one is called 0 and has to be different from 1, called a field. Well, if it's somehow, there are 2 group structures, the multiplicative group structure, the additive group structure, and they are compatible via the distributive law. So first, R with the addition commutative, say, neutral element. Zero. Then for the multiplication, if I take R without 0 with the multiplication, this is also a commutative group with neutral element 1. And the third one, as I said, is they are compatible by the distributive law. So that just is, if I take A times B plus C for all A. This is the structure. So obviously, you know many fields. Q, the rational numbers, the real numbers, the complex numbers are fields. And for instance, the integers are not a field because we don't have not every non-zero element is invertible. So I want to show that briefly that there are also some other fields. In particular, there are some finite fields. There are also finite fields. And I can, for this, I will do a little opposition, namely every finite integral domain is a field. But finite integral domain. It's quite easy. So if you have an integral domain, we have everything here except that we don't know that every non-zero element has a multiplicative inverse. So we only have to show that R star is equal to R without 0. So I call this integral domain R. So proof R star is equal to R without 0. So let's take an element. So let A in R without 0. We have to find an inverse. So we can look at the distributive law. So the distributive law says, I think I mentioned this in the beginning, that the multiplication by A from R with addition to R with addition is a group homomorphism. No, because precisely says that multiplication, no, this statement says that this is a group homomorphism. And so we have, it's an integral domain. So as R has no zero divisors, and our A here is non-zero, there's no non-zero element that if we multiply by it, we get 0. So that means the kernel of the multiplication by A is 0. So thus R is injected. So thus this multiplication is injective. But now we have an injective map from a finite set to itself. So it has to be surjective. A times surjective. So this thing is used very often. It's sometimes called Pigeonhole Principle, so that if you have as many boxes as you have pigeons that want to go into them, if there's no two in the same box, then all the boxes have to be full. And so this is this, and so this just means, so it's surjective. So in particular, one lies in the image. So thus, there exists an element C in R such that A times C 1. So that means. Okay, so this was this fact. And so in particular, as we do know already some finite integral domains, namely ZP, it follows that these are fields. So there, for example, for P a prime number, Z multiplication is an integral domain. Thus a field. So usually when one talks about this as a field, one denotes it differently. It's called denoted usually FP. One can, so we now know that there are some finite fields. So for every prime number, there is a field with P elements. One can actually show that there are more finite fields, namely for every power of a prime number, there is a finite field. We will see that later in the course. So actually, for every prime power, n, n elements. One can actually show that in a suitable sense, up to isomorphism, which I will introduce later, there is a unique field with p to the n elements for every prime power p, and these are all finite fields. But that we will see later. Okay, so I mean, one can also here see from this argument that one needs here that the integral domain is finite. No, we are using here that if this map is injective, it's surjective, because, for instance, an integral domain which is not finite are the integers, and it's certainly not a field. But still, you know, the multiplication with any element from z plus to z plus will be injective, but it is not surjective. Okay, so now we want to talk about homomorphisms, and I mean, obviously, whenever you talk about anything, essentially anything in mathematics, any kind of object, you're always interested in the homomorphisms between this kind of objects. So the maps between the things which are compatible with the structure. In this case, like with groups, the structure is that we have a set with two binary operations. So to be compatible with it means it must be compatible both with addition and multiplication. So therefore, the definition is obvious. I mean, there's that A and B be rings. A map A to B is called a ring homomorphism, it's compatible with addition and multiplication. In that sense, the sum to the sum and the product to the product. So if P of A plus B is equal to P of A plus B, and P of AB is equal to A times phi B for all A and B in A. Okay, so this is clearly definition. So now it's clear we had defined what a subring is. It follows immediately that the image of a ring homomorphism is a subring. So if you have a map phi from a homomorphism from A to B, then phi of A is a subring of B. So mark ring homomorphism, then phi of A is subring of B. Now, as in the case of groups, if the kernel, so what is the kernel of a ring homomorphism? So for a ring, in general, for a ring, we only have the neutral element 0 of addition. So the kernel is the inverse image of 0. And then we will have that the kernel of a ring homomorphism is also a subring of the source, but it's something better, which will be called an ideal. So the anyways, the definition. Kernel of the ring homomorphism from A to B minus 1 of 0. And it's, again, very easy to see. It's a subring, but it will be something better, namely an ideal. And so I want to introduce ideals, which are a very important concept, which one uses all the time when one uses rings. So definition. Subset I of a ring R is an ideal if it's first a subgroup of the additive group, and secondly, for the multiplication, it's something better than the condition one uses for a subring. So if I with addition is a subgroup of R with addition, and secondly, we have that for all elements A in I and all X in the big ring, we have that AX is an element in I and XA is an element in I. So I sometimes, for non-commutative rings, one uses only one of these two conditions and calls them left ideals or right ideals, but I'm not interested in those. I only interested in the case that both of these hold, which is called two-sided ideal. Anyway, very soon I will make the assumption that the ring is commutative, so that there's no difference. So you can see this is a strengthening of the condition of being a subring, because for a subring, you would have to assume that AX is in I if A is in I and X is in I. Here, instead, it's supposed to hold for all elements X in R. And so this is a strengthening of the condition of subring in the same way, in some sense, as normal subgroup is a strengthening of the condition of subgroup. And it will also lead to the fact that you can take the quotient of a ring by an ideal, but not necessarily, and this will be a ring, but you wouldn't be able to do this just for subrings. That later. In a moment. Let's first look. So, as I said, in particular, an ideal also a subring. Something better than a subring. Okay, so let's just look first at a few examples. So, example. So, in every ring, 0 and R are ideals. R in a ring R. Now this follows directly from the definition. So if A and B are ideals, then intersection is also an ideal. Follows directly from the definition. If you just look what it means, it's directly obvious. And same also, the same would hold if you have infinitely many ideals and take the intersection of all these ideals. This will also be an ideal. We can also instead, like we did for subgroups generated by some elements, we can also look at the ideals generated by some elements. So this is, I only do this in the case of a commutative ring with 1. So let R be a commutative ring with 1. And I take some elements. So the subring generated by these elements is given by all linear combinations with coefficients in R of these elements. So this is equal, so the ideal generated by, the ideal generated by A1 to AN in R is the set A1 to N, so I use the same notation as I used for subgroups, and now it's a set of all R1, A1 plus and so on, Rn. R1 to Rn elements in R. So by definition, it's clear that this would be an ideal because the sum of any two such things is of this form. You just sum the corresponding coefficients, Ri. And if you multiply such an expression by some element R in R, you just multiply every one of these by that R. And so you stay there. This is clearly an ideal. And it is also clearly the smallest ideal in R, which contains A1 to N. any ideal which contains A1 to AN, these elements A1 to AN, has to contain the ideal generated by A1 to AN. Okay. So one particular case of this is the ideal generated by one element. So similar like for groups, we had the cyclic subgroup generated by one element. Such a group is an ideal is called a principal ideal. Ideal of the form A. Note that this is just the same as A times R. Is called a principal ideal. And I think this is to some extent, I think that's the reason for the word ideal. So when ideals were introduced, you viewed them as some kind of ideal element of R. So if you have an element A in R, you can associate to it the corresponding principal ideal. So, like in some sense, it's another manifestation of this element A, and then the corresponding. So in that sense, an element in A gives us a principal ideal, but there are more ideals which I could view as somehow related to some ideal elements of R. That's how it was, classically viewed. But for us, so this is just a definition. I should say that so the ideals are very important for us, much more important than the subrings. So these are the things which actually one wants to work with. Okay, just maybe just a stupid remark. When do two elements give the same principal ideal? This they do if and only if they differ only by multiplying by a unit. So means so let R, so at least this is true in an integral domain. So let R be domain. Then, and we take two elements, A and B R, then the ideal generated by A is equal to the ideal generated by B if and only if there is a unit such that B is equal to the unit times A. There exists a U in R star such that B is equal times A. If one is in the integers, two integers define the same principal ideal if and only if one is plus minus the other. So, I mean, it's trivial, but I maybe still catch it. So if by A is equal to the ideal generated by B, then it means that if I look at it from here, B is an element in the ideal generated by A, so it's a multiple of A. So B can write A, B is an R, and in the same way, A is an element in the ideal generated by B, so A is an element in W times B is equal for some W in R. So thus, we have that, So for instance, A is equal to W times V times A. So as we are in integral domain, it follows that W is equal to 1. That means W is equal to V to the minus 1. And okay, so that was one direction. And the other direction is even more obvious. No, so if A, U unit, then it follows obviously that B is contained in A. So thus, the ideal generated by B is contained in the ideal generated by A, because just as the multiples of B must be contained in multiples of A. And also, we have that A is equal to U to the minus 1 times B. Thus, by the same argument, the ideal generated by A is contained in the ideal generated. So they're equal. Okay, so this was this simple fact. So now I claimed before that the kernel of a ring homomorphism always has to be an ideal. Now I will state that and prove. And we'll also do some kind of converse. So this is the following lemma. The most interesting part is the first, but anyway, let phi A to B be a ring homomorphism. Then the first statement is the kernel of phi is an ideal in A. Actually, we have a stronger statement. The inverse image of any ideal is an ideal. Generally, for any ideal I, B, we have that phi to the minus 1 of I is an ideal in A. Now, something which is a bit more special and not as important, but we will use it a bit, is that if the map is surjective, you also have some kind of converse. It says that, so assume from now also surjective ring homomorphism, then the map from the ideals in B the ideals in A, which contain the kernel of phi, kernel of phi is the inverse image of 0. Hope I wrote it. So which just sends our ideal I to the inverse image of I is a bijection. Okay. So, I mean, in fact, I will not do this in detail. I will just tell you what the inverse map is, and then one has to check that it makes sense. So with inverse, map from obviously the ideals in A containing the kernel for the ideals in B. Well, what's the obvious thing? You just take the image after the map. So J is mapped to phi of J. Okay, so maybe I will not check this. It's kind of straightforward. You just have to X it all out. So if you have an ideal in B, then you can see that if you take its inverse image, it will be an ideal. And obviously, as B contains the 0, this inverse image will contain the kernel, which is the inverse image of 0. And now, it's also quite easy to see if you have an ideal in A containing the kernel of phi, then its image will be an ideal in B, under the assumption that this is surjective. You have to use that it's surjective, otherwise it would be false. And then you can, if you look carefully, you can check that these are inverse to each other. One direction is trivial. If you take, which one is it? Phi of phi to the minus 1 of I, this will be I, always. And the other follows again from the fact that the map is surjective. But I leave that to you. I just now do the first part, which is easier but also more important. And it's almost trivial, but at least something I prove. So proof. So we take an ideal in B. Then, obviously, if I take phi to the minus 1 of J, this is certainly is a subgroup of A addition. We know that an ideal is a subgroup of B with the addition. So under phi is in particular a homomorphism for the subgroup with for the group with addition, and so this is clear. And now we only have to see the other thing, this with the multiplication. So let A be an element in phi to the minus 1 of J, and say X, we won't call it X. In an element. I want to know X an element in. Then phi of XA is phi of X times phi of A, obviously. This is an element in J. This is an element. So X is an element in phi minus 1 of B, which is the same. I don't need phi, just any element in A, sorry. So this is an element in B. It's a map from X to B, from A to B. So now this is, so that means this is an element in J, because J is an ideal. And so if phi of this thing lies in J, then it follows that phi of XA, that XA lies in phi to the minus 1 of J. And obviously the same way it works the other round. And similarly, is an element. And so phi to the minus 1 of J is an ideal. And obviously, okay. And so what is left to prove here is of similar level of difficulty, so I leave that to you as an exercise. So I want to, however, draw a few consequences, or just some simple consequences which we'll sometimes use later. So for instance, one consequence of this is that fields cannot contain non-trivial ideals. So that means in every ring we have 0 and the ring are ideals, but in the field these are the only ideals. So let me just state it. Mark that I in a ring be an ideal. Then if this ideal contains a unit, it's the whole of R. I is equal to R. Then the second is what I just said, that the only ideals K are 0 and K. And the third is a consequence of that, which is maybe the main way how one uses this statement. If I have a homomorphism from a field K to another ring, then it must be either injective or the zero map. So let K be a field from K to R be a ring homomorphism to a ring K, a ring R, then phi is injective or phi is equal to 0. That phi is equal to 0 obviously means that it maps every single element of K to 0 in R. Okay, and this is a quite simple remark. So let's assume we have a unit in I. Element in I intersected R star. Then we have an inverse, so we have 1 I can write as a to the minus 1 times a, and therefore as also an element in I, because a was in I, and so if I take any element b and for any element b in R, we have that b 1 b times 1 in AI. Okay, so this is trivial. And the other two are even more obvious consequences of this trivial fact. Namely, the second follows from the first by noting that the units in K are just K without 0. So if the ideal is not the 0 ideal, it contains a unit, and therefore it must be the whole of K. And the third one is that we note that the kernel of phi is an ideal. I forgot to say that. I mean, okay. Maybe I think I forgot to say that. But anyways, I say now the kernel of phi is an ideal in K. I don't remember whether I said it, but it follows. I should have said it anyway. This is this remark I've made when I introduced the kernel. So if phi from A to B is a ring homomorphism, then phi is injective if and only if the kernel of phi is 0. Here, because if you have a ring homomorphism, it's also a group homomorphism of phi with plus to B with plus, and we know that that is injective if and only if the kernel of phi is 0. So phi is also a group homomorphism A plus to B plus, and as such injective if and only if the kernel of phi is 0. And we had defined the kernel of phi as the inverse image of 0, which is precisely the same as the kernel of this map for with addition. So that's also clear. And then, okay, so the kernel is an ideal, and so the kernel of the ideal, as the kernel of this map of fields, starting in a field must be an ideal in K, and so it can either be 0, in which case the map is injective, or the whole of K, in which case the map is the 0 map. Okay, so I'm a bit, so I can maybe briefly introduce quotient of, one of the things that we don't like with normal subgroups in a group, you can also divide a ring by an ideal, and you still get a ring. That's somehow a nice thing about fields, that you can divide by them. And then you have also the corresponding homomorphism theorem. So now we define a quotient field, quotient ring, of a ring by an ideal. Definition R be a ring, I in R then, if I take I just with the addition, this is a normal subgroup of R with the addition, because it's a subgroup of R with the addition, but the addition is abelian. So it's a normal subgroup, so therefore we can form the quotient group. So thus can form the quotient group R mod I, just as usual the set of all cosets X plus I, X in R. and this is a group. With the usual addition. Okay, so this we already know. Now, in order to make the quotient, we want to have the quotient to make a quotient ring, so we have to define a ring structure in a natural way on it. So we have to see that this is also compatible with multiplication. So I write, just to save some time, I write just x for x plus I. And then what do we have? I can state this here as a proposition. That R is a ring. I an ideal. Then R mod I, the operations x plus y plus y as I had defined it, and the multiplication also just in a similar way, the multiplication of the coset of x and y being the coset of x times y ring. And furthermore, we have, if we look at the natural projection, that sends any element to its coset. Pi from R to R mod I sends x, and the class of x, so which was x plus I, is a ring homomorphism. Obviously, a surjective ring homomorphism. Okay, so there's not much. So we basically only have to see, like we had in the case of quotient by a normal subgroup, get the quotient group, that the multiplication is well defined. So we know that I take this R mod I, this is a group. And pi is a group homomorphism. For the addition. So we have to show that the product is well defined. So that means if I take if the class of x is equal to the class of x prime, and the class of y, class of y prime, we have to show that the class of x times y is equal to the class of x prime times y prime. Okay, so we just write it out. So what does it mean? That x is equal to x prime means that x minus x prime is an element in I. In the same way, y minus y prime is an element in I. And now, let's see. If we now look at xy minus x prime y prime, we have to show that that's also an element in I, then it's fine. So we do this by adding 0 in a nice way. So we have to, we say, I write this as x minus x prime times y plus x prime times, what is it? Y prime minus y. So if you look what we have done here, we have just added x prime y and have subtracted again. So it's the same thing. But now we see that this is an element in I. This is an element in I. So the whole thing is an element in I. And thus the multiplication is well defined. Thus xy prime y prime. So multiplication is well defined. And now it's trivial to see that, you know, the other axioms hold, so that we have the associative law. It just follows directly from the associative law in R. And distributive law follow directly from that in R. Okay, I maybe go 1 minute over to state also the homomorphism theorem, then we are done with the story on quotient rings. 1 minute means 10 minutes. So first, it's clear, well, maybe I don't do that. So we just have here the homomorphism theorem. For groups. So it's the usual statement, so let P projective group homomorphism with kernel K. Call the kernel now K, it's not a field, it's the kernel. Then the map phi bar from A mod I, which sends the class of X, or I could say X plus, so this was the kernel, X plus K mapped to phi of X is an isomorphism. I think I haven't directly introduced the word, but I mean it's clear that I defined what a homomorphism is. An isomorphism is a homomorphism which has an inverse, or which is the same as a bijective homomorphism. Okay, and so there's not much to show. So first one has to see that phi bar is well-defined and objective. That says, you know, X, the class of X is equal to the class of Y, if and only if the difference of X and Y lies in the kernel of phi. That's the definition of being in the same class. which is equivalent that phi of x is equal to phi of y. One phi of x minus y is equal to 0, which is equivalent to phi of x is equal to phi of y. And as we send here x plus k, or this class x, to phi of x, this means the map is well defined. So that if x is equal to y, then phi of x is equal to phi of y, and it's injective because it's if and only if. And then it's surjective by definition. We have, after all, defined in terms of the representative x, I've defined phi of x. Every x in A is allowed. And so, as the original map was surjective, also this map is surjective. And it's clear from the definition that this is a ring, clearly. Is a ring homomorphism. Now, if you just look at the definition, the product some x plus y is sent to phi of x plus phi of y, and the product xy is sent to phi of x times phi of y, and so it is a ring homomorphism. Okay, so thank you. So that's all I wanted to say for today. Are there any questions or comments? So, okay. So then I say goodbye for today and wish you a nice weekend.
Thank you.
Okay, thank you.